A startling development has shaken modern volcanology. Far out in the Japanese archipelago, on a lonely Pacific outpost named Uima, a sudden and dramatic event has reminded scientists that this island has never truly slept. Uima lies well south of Tokyo, about 777 miles away, often recorded in older local notes as roughly 200 to 250 kilometers, and appears on charts as a sharp triangle laid upon open sea. On paper it is small, about 5 miles, 8 kilometers, from tip to tip, and roughly 2.8 miles, 4.5 kilometers, across at its broadest point, a speck with an outsized story. Uima's Japanese name points directly to its chemistry. Sulfur Island, the label fits. The ground sits atop the rim of a flooded caldera, roughly 5.6 miles, 9 kilometers, across. The unseen engine that has been lifting the land year after year. For centuries, the island has been rising, not in a single jolt, but as a stubborn, measurable creep. Modern measurements put the average rate near 10 inches per year, about 25 centimeters. You can read that uplift in the rock itself. Wave-cut ledges carved in the 17th century now perch around 131 feet, 40 meters, above today's sea level. The island's most famous image is human, rather than geologic. The photograph of American servicemen raising a flag on the island's highest ridge, about 525 feet, 160 meters above the sea surface. That monument to effort and cost rests on volcanic scaffolding, piles of lava, ash, and broken rock that have been stacked, baked, and then lifted by a crust that refuses to stay still. The historic picture can distract from the restless background, whispering fumaroles, incrustations of elemental sulfur, and the faint, constant hiss of gas searching for daylight. On September 1st at 7:14 p.m. local time, the background became the main event. A sharp explosion opened new ground along the coast and turned a quiet shoreline into a theater of motion. Japanese researchers gave the fresh vent a name, Shidarama, and began documenting a scene that looked almost staged. A hole torn through coastal rock, a storm of fragments lofted and flung, and a plume climbing into the evening air. Dust-fine ash mixed with pebble-sized lapilli, orange with heat. Half-molten bombs arced upward and fell with heavy, perilous grace. The sound carried far over the waves, a rolling report that announced a system finding a new way to breathe. Local observers reported minor collapses along the new lava ledge, consistent with rapid erosion. What gave the blast its punch was the colliding chemistry of heat and water. Magma, well above 1,800 degrees Fahrenheit, 1,000 degrees Celsius, met cool Pacific seawater. The result was a sudden phase change. Liquid water flashed to steam on contact, expanding violently and amplifying the energy already stored in the melt. Volcanologists call such events phreatomagmatic, a word that can be unpacked to something like this. Magma plus water plus confinement equals shattering pressure. For minutes at a time, the shoreline behaved like a pressure vessel with a failing lid. Almost immediately, the sea began to carry away a second signal, pumice. Frothy, gas-rich melt, shattered and quenched into tan, bread-light rock full of sealed bubbles. Because it is so porous, pumice floats. It rides the ocean like rafts of cork. Whitish patches spread from the vent, then merged into drifting carpets that stretched in wavy sheets across the swells. Mariners learned to treat these belts with care. Pumice can clog cooling lines, abrade hulls, and hide hazards just below the surface. Overhead, the plume drew a layered sketch of the eruption's internals. Chalky white columns signaled steam, the water component. Gray curtains and darker bands betrayed suspended ash, the rock component. Watching that palette change in real time helps field teams judge the balance between water-driven fragmentation and direct magmatic discharge, especially when instrumentation is sparse at the coast. The outburst did not arrive without warning. In the weeks beforehand, island seismographs recorded strings of microquakes, too small for most people to feel, but unmistakable in the data. High-precision GPS and satellite radar showed the ground flexing by millimeters, numbers tiny in isolation, but loud in context. Deformation is the language of pressure. It is how a deep reservoir clears its throat. Fumaroles intensified. Their vapors, especially sulfur dioxide, the gas that smells of rotten eggs, rose in thicker streams. Gas tends to get out before magma does, so these plumes act like letters mailed from the subsurface, arriving days or hours ahead of larger news. A kitchen analogy helps. Take a sealed bottle of soda. Under pressure, the carbon dioxide stays dissolved. Release the cap and bubbles race upward, opening channels and pockets that were invisible a moment before. In many ways, magma behaves similarly. As pressure falls in parts of the system, dissolved volatiles unmix and seek escape. They pry open cracks, knit fractures into conduits, and can redirect the flow entirely. Uima's magma, rich in alkaline components, with trachyandesitic to trachytic tendencies, has the viscosity to trap gas and build pressure. That makes for eruptions that are especially explosive when water is involved. The caldera below Uima complicates everything. Instead of a single pipe beneath a single summit, the subsurface resembles a tangle of dikes and sills, side streets, rather than a highway. Existing vents do not own exclusive rights to eruption. Magma can thread an unmarked path, meet seawater at the edge, and construct a brand new opening. Shadorama appears to be exactly that, a shortcut to the surface that did not exist a day earlier, situated where fractured shoreline rock and hungry melt could meet. Is Shadorama the start of a longer sequence? It may be. New vents sometimes open in clusters, or one vent may wax and wane as supply shifts within the reservoir. The hazards in this coastal setting are blunt. Littoral systems can pivot from calm to life-threatening without generous lead time. Steam-driven jets can hurl dense blocks. Ash can blind navigators and choke engines. Pumice fields can mask collapsing benches and snag propellers. And the chemistry matters for people downwind. Sulfur-rich plumes can irritate eyes and lungs many miles away if the breeze carries them shoreward. Japan treats Uima and its cousins with patient attention rather than panic. Networks of seismometers, cameras, gas sensors, and GPS benchmarks feed into national watch rooms where shifts are mapped against experience. The goal is not to stop an eruption. No one can, but to understand it quickly enough to keep people and aircraft out of harm's way. When the coastline is the volcano's lip, notices to mariners must be nimble. Evacuation guidance must be clear, and pilots must have real-time plume advice before wheels leave the runway. The question of uplift returns again and again. Why does the island climb at all? Beneath Uima sits a reservoir that behaves like an inflating bladder. As fresh melt and gas arrive, the crust arches. Over decades, that subtle dome adds up to dozens of feet. Storms and waves record the change unintentionally. Sea caves that once met the tide now sit high and dry. Even the historic battlefield's contours owe something to this persistent breathing from below. Slow motion and sudden drama occupy the same address on Uima. Water, the island's constant neighbor, is also its impatient partner. It chills lava into glassy shards and flashes to steam with almost explosive eagerness. In many eruptions, the sea is a receiver of debris. Here, water is an active ingredient that pushes events into a different regime of violence. The spectacle can be breathtaking. Pillars of white and gray rising into evening light, glitter falling like snow in the plume's wake. But beauty is a poor safety signal. Distance and timing, not photographs. Keep people safe. This is not a call to alarm so much as a reminder about scale and tempo. The system that lifted 17th century shoreline markers 131 feet above today's waves is the same one that, on a September evening, opened a new vent where no map showed one, and lofted incandescent stones skyward. The past and the present share plumbing. For crews stationed nearby, for researchers, and for ships passing just offshore, the practical rule holds. Stay informed, keep clear when signals stack, and give the island room when it announces itself. Volcanoes teach in hard ways. Uima's latest lessons were plain. Microquakes are whispers. Deformation is a posted notice. Gas is a message from the deep, and the plume's colors are chalk on a blackboard. When those notes arrive together, shorelines can change in an afternoon. Today, the new name on the chart is Shidorama. Tomorrow, another may appear. In the end, Uima's September burst is more than a line in a field report. It is a living demonstration of how Earth's interior sends signals to the surface through pressure, heat, water, and fractured rock. Here, fire and sea share a boundary and sometimes collide. Respecting that rhythm is not superstition. It is literacy in a place built by forces that move whether or not anyone is watching. It's starting to feel like mountains everywhere are loosening at the seams. If you've been tracking the recent run of rockfalls and slope failures, you're not alone. Share your take below on what this means for mountain belts and their valleys worldwide. Let's focus on one case study, Hawk Vogel, rising to roughly 8,500 feet, 2,592 meters. It stands apart in the eastern Algae Alps on the Bavaria-Tyrol line, a solitary summit that dominates lower neighbors. Long before official records caught up in 1818, local shepherds were already on its ridges. Surveyors later used the peak as a triangulation point during early mapping efforts, proof of how prominent and reliable a landmark it once seemed. That appearance of permanence hides a touchy geology. Hochvogel is built mostly of Maine dolomite, a Triassic-age sedimentary rock. It's tough on the whole, but under the right stress, water, and temperature conditions, it can fracture and fail. History bears that out. On May 27, 1935, a massive failure ripped from the southwest face, sending thousands of cubic yards, thousands of cubic meters of rock downslope. More modest slips followed in 2005, 2007, and 2016. In other words, instability here isn't new. What's changed is the pace and scale of warning signs. The headline issue today is a summit-spanning crack that has been widening and deepening. Earlier measurements described a fissure about 130 feet, 40 meters long, approximately 10 feet, 3 meters wide, and approximately 26 feet, 8 meters deep. By 2024, high-resolution monitoring indicated dimensions on the order of 115 feet, 35 meters, in length, nearly 20 feet, 6 meters across, and roughly 20 feet, 6 meters deep. If a major section lets go, estimates suggest as much as approximately 340,000 cubic yards, approximately 260,000 cubic meters of rock could detach. Enough volume to reshape a valley floor and strip trails, alpine meadows, and infrastructure in its path. Since 2014, geoscientists and engineers, principally from the Technical University of Munich and the GFZ Research Center in Potsdam, have run an advanced warning network known as Alpsense Bench. Think of it as a digital nervous system for the mountain. Laser scanners, geophones, crack meters, GPS, and a continually updated 3D twin-track tiny movements down to hundredths of an inch, tenths of a millimeter. The system's goal isn't fortune-telling, it's pattern recognition. When motion accelerates in ways that typically precede failure, the instruments can flag danger a couple of days in advance. Like a weather forecast, it can detect trends and tipping behavior, but it cannot name the exact hour a block will break. Despite the warnings, curiosity draws people in. Hikers still edge toward the open fracture to see the problem up close. That uneasy mix, spectacle and risk, has turned Hochvogel from an icon of alpine beauty into a live hazard zone and one of the most closely watched mountains in the range. Seasonal conditions amplify the threat. As European summers warm, accelerated snowmelt and heavier rain load the rock mass with water. Rain infiltrates joints and bedding planes, acting like a lubricant, while also adding weight. Over the past 5 years, the crack's width has grown by about a foot, approximately 30 centimeters. A small number on paper, but alarming at this scale. The situation echoes a Swiss case near Blatten, where a slope's movement rate jumped from approximately 0.5 inch per day to approximately 0.5 inch per hour, an escalation that made collapse imminent. That is exactly the kind of acceleration the sensors here are tuned to catch. If a major release occurs, modeling suggests debris could surge into Austria's Hornbach Valley near the Germany border. Population in the direct path is sparse, but there are well-used trails, huts, and grazing areas. The consequences for those sites could be severe, even if towns farther away remain out of reach. To manage that risk, authorities have tightened early warning procedures so that rescue teams, alpine clubs, and local administrations on both sides of the frontier receive immediate alerts. With even 2 days' notice, priority areas could be cleared to prevent casualties. One event may not be the end of it. Specialists expect a stepwise breakdown as possible. Phases of failure spread over months or years. That kind of drawn-out destabilization would keep access limited and require continuous monitoring, with ripple effects for tourism and the local economy tied to mountaineering and hut networks. There's also the human layer. For communities that have lived with the mountain as a backdrop, a place of quiet and challenge, the present uncertainty carries a psychological toll. Trails that once felt routine now demand vigilance. The landscape itself feels provisional. Zooming out, Hochvogel's behavior fits a pattern seen across the Alps. In recent decades, extreme weather has become more frequent. Intense rain, hotter summers, and volatile storms. Lightning is under investigation too. Repeated electrical strikes can micro-damage rock, and when you combine that with prolonged saturation from rain, the structural integrity of fractured dolomite can degrade over time. It's death by 1,000 cuts. No single factor explains it, but together they tip the balance. Monitoring continues around the clock. Millimeters matter here. A slight jump in displacement speed can separate, stable enough for now, from failure in progress. And the hazard isn't only rockfall. Should a large collapse occur, secondary debris or mud flows could mobilize later, potentially traveling into the Hinterbach Valley and creating follow-on dangers. That's why planners are already sketching longer-term protections, not just emergency responses. Add it all up, climate trends, the natural fatigue of an old mountain, human exposure, and the slow arithmetic of geology. And Hoch-Vogel has become a working laboratory. It's no longer just a summit to photograph or bag. It's a case study in how fast solid ground can change. The old cliché, solid as a rock, doesn't land the way it used to when the rock is riddled with widening joints and measurable motion. What does feel solid is the need to respect both the landscape and the science watching over it. If stories like this catch your interest, stick around, subscribe, tap the bell so you don't miss new deep dives, and pass this along to friends who follow natural hazards. And tell us in the comments what you make of the Hoch-Vogel situation, or if you've seen similar slope instabilities on your own travels. Your experiences help widen the discussion. For those who want a little more technical context, consider the mechanics at play. Main dolomite typically features bedding parallel weaknesses and vertical fractures formed over geologic time. Freeze-thaw cycles widen those voids as water expands into ice, and in warmer seasons, infiltrating rain reduces friction along those same plains. Add the occasional seismic vibration, regional earthquakes, or even distant tremors can contribute, and you have a system primed for episodic movement. Each episode need not be catastrophic on its own, but cumulatively, they can reduce the safety margin until a nudge, an intense storm, a temperature swing, or a saturated week pushes the mass beyond its threshold. That is where monitoring earns its reputation. Laser scanners map the face repeatedly, comparing point clouds to detect subtle bulges or overhang growth. Geophones listen for microcracking, tiny acoustic emissions that hint at bonds failing within the rock mass. Crack meters measure aperture changes across the fissure, while GPS monuments track surface displacement. Feed all that into a living 3D model, and you can see which blocks are moving coherently and which are locked, giving responders a target for closures and evacuations that is grounded in data rather than guesswork. The goal is not to eliminate risk, no one can, but to convert uncertainty into informed decisions that save time and lives. The social piece matters too. Messaging must balance clarity and proportion, neither downplay nor sensationalize. Local guides, HUD operators, and municipal leaders succeed when communications are simple, timely, and consistent. Close today signs need clear detours. Alert levels should be color-coded and explained. Evacuation drills should be practiced in shoulder seasons when routes are less crowded. Small choices like multilingual notices or QR codes linking to live dashboards can save minutes when minutes matter, and visitors can help by treating closures as lines not to be crossed rather than challenges to brag about online. Finally, remember that mountains change on human timescales more often than we think. The Alps are not static museum pieces. They're dynamic landforms shaped by uplift, weathering, ice, water, and gravity. Hoch-Vogel is a reminder that beauty and hazard live side by side. Respect the forecasts, heed the ropes, and treat that widening crack not as a spectacle, but as a message from the rock itself. As we wrap up, a quick note on personal responsibility. If you visit this area, plan conservatively. Check current closures, register your route when required. Carry a map and headlamp even on fair weather days, and turn around early if the ground or the forecast feels wrong. The summit will be there tomorrow. Your margin for error may not. Sicily's towering fire mountain looms over the island's east like a restless cathedral. Mount Etna in southern Italy is not only large by European standards, it is the continent's most energetic volcano, a place where the crust moves and sometimes roars. Its summit stands near 10,825 feet, about 3,300 meters, though the exact number shifts with each outburst as craters build and collapse. For centuries, Etna has cycled through eruptions and pauses, becoming both a research site and a major attraction. That appeal comes with a sober reality. Beauty and danger share the same slope. Etna's behavior does not follow one simple script. It moves along a spectrum, from modest strombolian pops and ash puffs to short, intense episodes that fling columns of molten rock skyward. In the latest chapter, fresh lava has again threaded down the flanks, cutting glowing rivers through black scoria, while orange fountains light the night. Authorities tightened access, keeping people below roughly 8,200 feet, about 2,500 meters, while instruments flagged elevated shaking. The goal is straightforward: admire the show, but keep distance while the mountain's pulse is high. A new feature has become the focal point of concern: a visible fissure on the upper slope. Drone surveys and handheld footage make the crack unmistakable. This is not a surface blemish. Fractures like this reflect underground stress as pressurized magma pries rock apart. Such openings can precede larger events, lateral eruptions lower on the cone, or, in more severe cases, structural slumps that peel away portions of the flank. Scientists have long measured a slow, persistent slide of parts of Etna seaward, a creep that usually proceeds at a walking pace each year, but hints at the forces at work inside the edifice. In rare cases elsewhere, sudden volcanic slope failures have even kicked up waves. That is not a forecast for Sicily, but it explains why a new crack instantly raises the stakes for monitoring. Even as lava fountains and glowing streams seize the eye, the volcano's internal heartbeat, the tremor signal, continues. It strengthens and dips, but together with surface deformation, it points to a system under pressure. Volcanologists are asking a simple question with complicated implications. Is this a familiar pulse in Etna's rhythm, or the start of a deeper reshaping of the mountain's plumbing and flanks? The fracture sits just below the summit crater complex, in what specialists call a subterminal zone, near the 3,000-meter contour. That belt is notorious among Etna watchers, because stress can accumulate there until the volcano chooses a side vent instead of the summit. Flank eruptions are disruptive. They can open abruptly, cross trails and roads, and send lava toward valleys long unused to flows. Their unpredictability raises risk for hikers, workers, and nearby communities alike. Ground sensors show deformation consistent with magma intrusion, hot material wedging into cracks and lifting the surface. Bi-amount satellites detect even when people notice nothing. The new fissure is likely the surface expression of that push. If intrusion continues, modest activity can escalate into stronger paroxysms, or if rock fails, into local collapses. Recent aerial passes mapped several small vents feeding multiple lava tongues. As they descended, the flows split and rejoined like braids in a river. The farthest fronts reached about 7,546 feet, around 2,300 meters. Higher up, the summit vents above, roughly 9,843 feet, near 3,000 meters, continued to supply fresh magma, turning the upper slopes into a moving assembly line of incandescent rock. In parallel, Italian civil protection raised the alert posture. An F1 advisory signals heightened caution and keeps the summit effectively off-limits. Should conditions escalate to an F2 stance, as happened earlier this season, authorities would warn about fast-moving hot clouds and sudden hazards. A recent dip in seismic chatter may look like relief, but lulls on Etna often precede bursts. Paroxysmal episodes, sudden violent releases of pressure, can drive sky-high lava jets, loft tall ash plumes, and blast glowing clasts across wide arcs. Those clasts, called lapilli volcanic bombs, can be as small as gravel or as large as a football, and they travel fast. On busy volcanoes worldwide, people have been injured by projectiles and ash clouds that outran expectations. A grim lesson from New Zealand's Wakari/White Island is that a volcano in routine activity can still switch gears without much warning. Etna is more active than most, so that lesson applies doubly here. Part of the management challenge is Etna's shape-shifting tempo. A cycle can start with tame spattering, leap into fountains, toss short-lived pyroclastic surges, then fall back to a simmer. The newly mapped fracture could mark a deviation from that familiar arc, hinting that structural stress is accumulating in a way that increases the odds of a lateral opening. Italy's National Institute of Geophysics and Volcanology reports ongoing strombolian bursts at the summit with intermittent ash visible from surrounding towns. Analysts watch more than camera images. They track the precise height of advancing lava fronts, monitor the rise and fall of harmonic tremor, and listen for infrasound signatures that reveal explosions even when weather hides the vents. Together, those metrics show magma still moving underground and feeding the surface. Because the system is unsettled, caution is wise. No one can say with confidence how the next day or two will unfold, and that uncertainty is itself a warning sign. Persistent tremor, active deformation, a fresh fissure, and multiple lava sources argue for restraint on the mountain and vigilance in the communities below. A new vent can open with little notice. An existing vent can choke and then clear with more force. Wind can swing an ash plume over a road that was clear an hour earlier. Sicilians have lived with that reality for generations. Ash on the windshield at breakfast and a faint glow on the horizon after sunset are part of the local rhythm. When instruments show rising risk, authorities close trails and restrict access. The latest fracture, together with pressure signals, argues for a stretch of heightened respect. Being prepared, knowing routes, keeping masks, having a communication plan is not alarmist. It is responsible. Round-the-clock monitoring continues. Networks of seismometers listen for swarms, too small for people to feel. GPS receivers and tilt meters register millimeter-scale motions of the ground. Thermal cameras chart the heat of flows and vents. Gas sensors measure sulfur dioxide and other emissions that rise when new magma nears the surface. Drones supply overhead views that ground teams cannot get safely. Together, these tools give a near real-time portrait of Etna's mood and help officials adjust closures and guidance. The broader scientific community follows closely because each Etna cycle teaches lessons that travel. Comparing data from Sicily with other regions sharpens models of magma ascent, flank stability, and the thresholds that tip a photogenic eruption into a hazardous one. In that sense, every measurement taken on Etna contributes to the global understanding of how our planet moves heat and material from its depths to the surface. For visitors and locals, the advice remains simple. Enjoy the spectacle from safe lookouts and respect guidance from the park and civil protection. Keep clear of summit zones. While the alert is elevated, the mountain's beauty is real, and so is its unpredictability. Respecting both is how you witness the show, without becoming part of the response. If you're passionate about geology and want more updates as this sequence evolves, stay tuned. We'll keep translating measurements and field notes into plain language. Share your thoughts below. Do you think this fissure signals a larger shift, or will Etna settle back into its familiar cadence? Your perspective helps guide what we explain next, and your caution helps keep everyone safe on the slopes. Quick glossary. Strombolian means rhythmic bursts from gas bubbles at the vent, spectacular but typically limited in range. A paroxysm is a short, powerful peak that can hurl lava high and spread ash widely. Pyroclastic flows are fast, ground-hugging clouds of hot gas, ash, and rock. Rare on Etna, but dangerous enough to drive higher alerts. Lapilli are small cinders. Volcanic bombs are larger blobs that harden in flight. Terms like these explain why rules can change quickly. Last point, volcano science is probabilistic, not prophetic. Analysts merge many weak signals, small gas shifts, subtle tremor, centimeters of tilt, into a picture of rising or falling risk, then revise it as new data arrive. Patience with restrictions and respect for the mountain make safer outcomes possible. Stay informed, stay flexible, and give Etna space.